Earth's magnetic field plays a vital role in protecting life on the planet. Without it, Earth would be bombarded by harmful solar winds and cosmic radiation, making life as we know it impossible. This invisible force field surrounds our planet, extending from the Earth's core out into space, forming what we call the Magnetosphere. But where does this magnetic field come from? It originates deep within the Earth's interior, in the core, where complex processes generate the field in a phenomenon called the Geodynamo. Earth's magnetic poles, located at the north and south ends of this field, aren't fixed. They move and even switch places in an event known as a pole reversal. In this video, we'll explore how Earth's magnetic field works, how pole shifts occur, and what their potential effects could be on modern technology, nature, and human life. Understanding these processes is crucial for grasping the dynamic forces that shape our planet and how they impact life today and in the future. Earth's magnetic field is generated by a process known as the Geodynamo. This process takes place deep within the planet, specifically in the outer core, which is made up of molten iron and nickel. The outer core surrounds the solid inner core, and the movement of this liquid metal is what drives the magnetic field. Convection currents in the outer core, due to the heat from the inner core and the cooler mantle above, hot molten iron rises while cooler material sinks, creating convection currents. This constant motion of conductive liquid metal generates electrical currents. The Earth's rotation influences the direction and flow of these convection currents, causing them to swirl in specific patterns. This rotation, combined with the movement of the molten iron, is critical to sustaining the magnetic field. As the molten iron moves, it carries with it charged particles. The motion of these charged particles creates electric currents, which in turn generate a magnetic field around the Earth. This is similar to how electric currents in a wire generate a magnetic field around the wire. The magnetic field that results from this process extends beyond the planet's surface, creating a protective bubble known as the Magnetosphere. This magnetosphere deflects harmful solar radiation and charged particles from the sun, preventing them from stripping away our atmosphere and causing widespread damage to living organisms. The Geodynamo is a complex system that has been functioning for billions of years, but it is not static. The strength and structure of the magnetic field change over time, which leads to phenomena like the shifting of the magnetic poles and occasionally a full pole reversal. Understanding these changes requires a deeper look into the behavior of Earth's core and the history of magnetic pole shifts. Earth's magnetic poles are not permanent. They have shifted and even reversed many times throughout the planet's history in an event known as a magnetic pole reversal. This means that the magnetic North Pole becomes the South Pole and vice versa. These reversals have occurred numerous times, with the last major one happening approximately 780,000 years ago. Pole reversals are not sudden events. They happen gradually over thousands of years. During this process, the magnetic field weakens, shifts, and eventually stabilizes with the poles in opposite positions. The weakening phase is particularly important as it can leave Earth more vulnerable to solar radiation and cosmic rays. The reasons for pole reversals are still being studied, but they are believed to be caused by changes in the flow of molten iron and nickel in the outer core. This flow is not perfectly stable, and over time, turbulence or disruptions can lead to the magnetic field weakening and flipping. During a reversal, Earth's magnetic field doesn't disappear, but it weakens significantly. This reduced strength makes the planet more susceptible to solar winds and cosmic radiation, which can penetrate the weakened magnetosphere. As the magnetic field weakens, more charged particles from the sun and outer space can reach Earth's surface. This increased radiation could impact satellites, telecommunications, and even human health, especially for astronauts and airline passengers flying at high altitudes. During the transition period, the magnetic field becomes more complex. Instead of having clear north and south magnetic poles, multiple magnetic poles may emerge in different locations around the globe. These anomalies could confuse animals that rely on the magnetic field for navigation, such as migratory birds and sea turtles. The weakening and shifting of the magnetic field could interfere with GPS systems, satellite communications, and power grids. A weaker magnetic field might allow more solar storms to affect these systems, leading to potential blackouts and communication issues. While a magnetic pole reversal may seem alarming, it's important to note that these events have occurred many times in Earth's past without catastrophic consequences. However, understanding how they happen and what to expect during a reversal helps scientists prepare for potential disruptions in modern technology and communications. One of the biggest concerns during a pole shift is its effect on technology. The weakening of the magnetic field could leave our planet more exposed to solar flares and geomagnetic storms. These powerful bursts of energy from the sun could disrupt satellites, GPS systems, and communication networks. For example, a strong solar storm could cause power outages, interfere with flight navigation, and damage satellite infrastructure. Increased cosmic radiation due to a weakened magnetic field might have health impacts, especially for astronauts and people flying at high altitudes, such as airline pilots and passengers. Earth's atmosphere would still provide some protection, but the rise in radiation exposure could lead to a slight increase in the risk of cancer or other radiation-related illnesses for those consistently exposed. Many animals, such as migratory birds, whales, and sea turtles, rely on Earth's magnetic field to navigate long distances. During a pole shift, the weakening and possible reorganization of the magnetic field could cause confusion for these species, affecting migration patterns and possibly leading to disorientation. Although there is no direct evidence that a pole reversal would trigger large-scale environmental disasters, the increased exposure to solar radiation might slightly alter weather patterns or cause localized disruptions in climate-sensitive regions, especially near the poles. The process of a magnetic pole reversal is a natural and recurring phenomenon, though it takes thousands of years to fully unfold. While the exact timing of the next pole reversal is uncertain, the ongoing study of Earth's magnetic field helps scientists better understand when and how such events may occur. In the modern world, a pole shift might have more noticeable effects due to our heavy reliance on technology and global communication systems. However, with advancing technology and greater scientific understanding, we are becoming more capable of predicting and mitigating the impacts of such changes. Ultimately, Earth's magnetic field has protected the planet for billions of years, and even with a pole reversal, life on Earth has thrived through these shifts before. Scientists will continue monitoring the magnetic field closely, ensuring that we remain prepared for any disruptions, while also studying how the geodynamo and magnetic field may evolve in the future. By understanding Earth's magnetic field and its potential changes, we can appreciate the vital role it plays in shielding life on our planet and the fascinating dynamic nature of our world.